Good morning, Lambda days. You're supposed to say good morning back. Thank you. So I very much appreciated John's talk this morning. I would have appreciated it more if he'd referenced a few of my papers, but I did like the bits about combining operations and about there being fundamental laws, because that's what I'm going to tell you about in my own presentation. So a quick poll of the audience before I start. Who knows about parallelism? Good. Oh, well, great. Who knows about types? Excellent. And who knows about hylomorphisms? Whoa. And who knows about parallelism, types, and hylomorphisms? Aha. Thank you, Adam. So this is what I'm going to be presenting this morning. The material is a bit technical, but I'll try to explain it in fairly general terms. And if anything isn't clear, please do ask me questions, probably at the end of the session. So what's the motivation for this work? Well, patterns are great. In the parallel programming community, parallel patterns are particularly great because they help us with structuring our code. However, for a given parallel pattern, what we need to do is we need to choose the best implementation. And that means that we need a way to reason about the structure of our parallel programs. Now, in a previous paper that my colleague David Castro presented at ICFP earlier this year, what we did was we showed you how to deal with the correctness of the transformations. And what we've been doing in the work that I've presented to the special issue of FGCS is then to reason also about the performance of the program. So these two things are complementary. Firstly, reason about the structure, done that. Now, reason about the performance, and put the two things together. Now I've got a complete system for reasoning about the structure and performance of a parallel program using a type system. So firstly, I'm going to tell you a bit about skeletons. So there are a number of common patterns of parallelism that we crop up all the time in the parallelism community. One very common one is a so-called task farm. What happens with a task farm is you have a number of inputs, and the inputs are divided amongst a number of workers. Each of the workers can work in parallel, and then the results are collected up and passed on. Okay? It's a very simple kind of skeleton. Turns out to be very, very common. And this way you can replicate operations. So you've got some F, you can replicate it. Another type of common skeleton is a pipeline. And with a pipeline, what happens is, you're all familiar with these things from undergraduate days, I expect. You have some input coming in, some operation F works on the input, produces some result in an intermediate form, that gets picked up by a second stage in the pipeline, a G, that does its stuff and produces the result. And what's nice here is that F and G can both work in parallel, provided you have some kind of buffering in between the two pipeline stages so they don't bump into each other and they can operate at the same time. So this is another common skeleton. It turns out that there's a bit of theory from the parallelism community that says that if you've got pipelines and farms, you can do everything. Well, actually, we think the theory says you can do almost everything. And we showed you could do a bit more than they could do in our previous paper. So I'm going to give you an example of what we're trying to do. I've got a little function, an image merging function, and what an image merge does is it works over a list of pairs of images. So here's the type here. The thing to the left of the arrow is the input type, list of pairs of images. And what we're going to do is we're going to give, as a result, a list of images. I'm sorry, John, this is not Haskell. It's Haskell-like, okay? But I hope you can forgive me for that. So list of pairs of images coming in, list of images coming out. And what are we doing? Well, what we're doing is we're mapping over all of the input lists in one after the other, and we're applying first a mark operation and then a merge operation. So we've got a sequential composition of a mark and a merge operation. Now, it turns out that even given this incredibly simple definition, there are many possible parallel implementations just using farms and pipelines. And I've listed a few of them down here. So image merge 1, you've got a farm over some function of the merge and the mark. So I've collated the merge and the mark together as some base functionality, and then I've farmed over it. And I've got n copies. Okay? So I can have n things working on the inputs in parallel. Brilliant, simple. Or I could have two farms working together. I've got a farm of n, size n, a farm of size m. They don't have to be the same size. So we've got n workers on the mark stage, pipelined into n workers on the merge stage, and so on and so forth. And the question is, which of these is the best thing? Okay, and that's the question we're trying to answer. But first, a digression. Why do we care about types? I'm waiting for John to tell me something. Well, according to the types community, we care about soundness. Well-typed programs cannot go wrong, whatever wrong means. And there's a whole series of PhD theses on that. And documentation, which is that type signatures provide valuable documentation to the programmer. But what we really care about, from my perspective, is that well-typed programs can be parallelized as described by the types. There's an operational interpretation of the types that tells us about the execution of the program. And moreover, the type-level parallel structures clearly separate out what's happening in the parallelism from what's happening in the functionality. Thing John was saying earlier, separate two things. Specialism, the types tell us about the structure of the parallel program, and the code tells us what the program is doing. Simples, isn't it? So why has nobody done it before? And finally, the great thing about types is we don't have to do it all ourselves, because some very, very clever people like Phil Wadler and other people have come up with really great unification algorithms and type systems. So we can just pick that up, Edwin Brady with Idris. So you can just pick up all that clever stuff and use it, and we don't have to build our own stuff. Fantastic. I'm always in favor of stealing other people's work when I can. So I've got my image merge function, and what I want to do is to parallelize it. Well, how am I going to do that? What I'm going to do is I'm going to decorate the type, the function type, with some blurb, IMNM, some caveat, and that's going to tell me a bit about the parallelization. So the stuff in red is now the parallelization, a bit like a type class, if you're familiar with those in Haskell. So if I define IMNM to be the stuff in red, the farm of n over some function of type A, and farm of m over some function with also of type A, then what I've done is to define one possible parallel implementation simply by specifying the type. And now I can automatically use the type system to rewrite my source code to introduce the parallel execution that I want. All I have to do, change the type, click. We've got a parallel implementation that corresponds exactly to that parallel structure. Or you change it to some other type, and you get some other implementation. And we can guarantee from the underlying laws of functional programming that what we've got is functionally equivalent to the original parallel version. Okay? If you've done any parallel programming, you realize just how hard it is to know that the program you end up with is the same as the one you started with. Race conditions, deadlocks, all that stuff, but we know because we are functional and we have laws. So how do we introduce our parallel patterns? Well, what we do, start in the top left, we've got the original program structure. You might think of that as being sequential, but it doesn't actually have to be sequential. It's just what you started with. If we normalize it into some canonical form, we can then rewrite the canonical form according to some laws, which are in the ICFP paper and the upcoming FGCS paper. And then we can go backwards, and we can end up on the right-hand side with the parallel program that we want. Okay? So the type system is driving all of this transformation. The type system says you go from here to here. That means there's a rule, there's a corresponding rewrite rule, and the type system can perform that rewrite rule for us using its normal mechanisms. So, question. How do we decide when two things are the same? Well, I mentioned hylomorphisms at the start. We use hylomorphisms, which have strong laws and properties. So a hylomorphism is a generalization of a divide and conquer. If you've got a hylomorphism over a G and an H, then that's defined as doing a G, applying some F, and then doing the H. What's happening is that the G part is a split part in a divide and conquer. The F is the operation you're applying, and then the H part is doing the combine part in your divide and conquer. So a hylomorphism is simply a generalized divide and conquer. And it turns out that the skeletons I described to you can be defined as instances of hylomorphisms, which is very cool. So here's a little example. Quick sort. If you start off with a type T, and the T is the three parts that you get when dividing a quick sort. So you've got the pivot, you've got a left sublist and a right sublist, left sublist type list of A, right sublist also a list of A. Then we can find a quick sort to be a hylomorphism of a merge and a split, where the merge is going to take the result of the sort and put things together. And the split is going to start off with our original list and split it down so we've got the pivot and the two sublists. Now we've completely defined a quick sort algorithm just using a hylomorphism. Cool. If we now start with a streaming sequential version of this, so we're mapping that over a list of inputs, what we can now do is, if we want a version using task farms and pipelines, we change the type, the special bit on the type, to say, oh, well, it's a parallel implementation with a farm, pipelined with something else. And notice I've left some underscores in the type to indicate there are holes there. We don't care in our type what they are. We'll let the type system figure it out. That's what type systems are good at, after all. They're good for figuring out the stuff I don't want to have to think about, discuss. Or, if you want to create a divide and conquer version, all you have to do is change the type again. So all we have to do is to say, well, we want a parallel implementation, and now we want a divide and conquer algorithm rather than the pipeline and farm version. And we can see trivially, because a hylomorphism is really a divide and conquer generalized, well, of course you can get a divide and conquer out of that. And likewise with the farms, etc. We define a base semantics for our programs using some well-known recursion schemes. So these are things that I hope everybody uses every day in their programming. So maps, who uses maps? Good. Folds? Oh, good. Unfolds? Aha, that's what I expected. Plus sequential composition. So maps, folds, unfolds, these are very common patterns that we find in our software. It turns out that you can define the semantics of the operations we want in terms of these base things. So our denotational semantics I've abstracted here. The interesting things to show you are that a pipeline, semantics of a pipeline, is just the semantics of composition. So the second line down in my semantics there, we're just composing two things to get what happens functionally. The semantics of divide and conquer is simply the composition of a catamorphism that is a fold, I always get this wrong, with an anamorphism that is an unfold operation. So first we're unfolding, then we're doing stuff, and then we're folding. And that's a divide and conquer, as you'd expect. And then to lift these things up to the parallel level, as I showed you, what do? Well, you put in a map. And now we're streaming over a series of inputs. So now I've got a parallel version. If we want now to work out are two parallel programs the same, all we have to do is to erase the parallelism from the original program, work out what the sequential structure is, transform the sequential structure by saying, well, we've got some form in terms of hylomorphisms, so let's transform it into another form of compositions of hylomorphisms, reverse that back up to the parallel structure we want, and now we can just automatically transform one parallel structure into another. It turns out that recursion schemes are hylomorphisms. So all of these recursion schemes, maps, catamorphisms, anamorphisms, these are all instances of generalized hylomorphisms, divide and conquer type things, where you might put in an identity operation, for example, in the anamorphism, because you don't really care about that part of the divide and conquer, the hylo. We had a eureka moment in my office when we discovered this. It's turtles all the way down. So, as I said, what we can now do is to leave some holes in the types. Underscores are the holes that we want to be filled in. The type inference mechanism, type unification, is going to replace the underscore with any suitable parallel structure. So the bits we've specified have to be unified with the actual type, but then the underscores, well, we can just fill those in. Or we can actually write type-level functions. If you're a dependently typed person, you'll see this is easy to do. So we can, for example, write a type-level function that says, well, given this structure, a pipeline with something first and then a farm, what is the least cost structure that you can infer for that? And the type system will go away, it will do its stuff, it will use a dependent type or other type inference mechanism, and it will say to us, yeah, okay, here's the operation that gives you the least cost. And all you have to do, and this is the topic of our new paper, is come up with a good cost model. Thanks, John. And that's what our new paper does. What it does is to build a model for skeletons in terms of queue structures and explain how you can come up with amortized costs for each of the operations. So here's an example. What I'm doing here, I've got the cost of the farm, and what we're doing basically is replicate the farm n times. The capital Qs are the input and output queues in each case. So what we're doing is we've got an operation P, we started with Q0, Q1, and basically what we do is we replicate it n times, original input queue, original output queue, merged somehow by the implementation. We've then got n copies. We can work out what is the cost of each PQ. So basically it's the time to do the operation, pretty obvious. Some DQ time, take the thing off the input. In Q time, put the result onto the output queue. And if you've got n of them, then the amortized cost is just that divided by n. Okay? Simple. But does it work? Okay. Now, if I was a theorist and doing my PhD, I would say, yeah, okay, that's it, done, problem solved. I don't need to do that. But hey, I'm really a practitioner pretending to be a theorist. So let's have a look at what this does. What we've got here is we've tried some examples. This is a simple matrix multiplication running on a 24-core AMD Optron machine from our colleagues in Italy. And the solid red line is the predicted, sorry, it's the actual performance. The dashed red line is the predicted performance in terms of speed up on these cores. So you'll see that we're getting something like a 17 times speed up on 22 cores, and we're predicting something very, very similar. And we've tried this for a number of examples. It's not just one flash in the pan. Here's another example, a bit more complicated structure. What we've got here is a pipeline, the double bar is the pipeline, 2 farms over 2 functions, and we've varied the number of workers, the N1 and the N2 in each case. And what you can see is, again, that our cost model gives us very, very solid predictions of all of the costs that we're getting. Okay, so it's a very good predictor in this case. Moreover, each time the number we're predicting is below the actual number, so we have a high degree of confidence that we're not over-predicting, giving you something which is realistic and you can rely on. Pretty good. Or if you have different structures, this is just to say the structure really doesn't matter on the same program, well, again, we can predict the performance and compare this with the actual performance for each of these structures. And you'll see that in this case, the prediction is almost one-on-one with the actual performance that we observe. So we're getting good predictions for different structures. That's great. If we always said the same thing, our cost model would be pretty rubbish. And this is another example, and I've extended it up here to 64 cores, and what we're able to do, it's an image convolution, and what we're able to do is to predict the best performance about 56 times on a 64-core machine for our example. And we were able to say to you, well, this thing farm over a pipeline, actually that isn't very good, because you're only going to get about 23, 24 times speed up, and hey, it's going to tail off. Okay? So we're getting some real usable predictive power, able to tell you what is the best solution. Conclusions. So deriving the costs of parallel structures from operator semantics is incredibly powerful. You can automatically derive cost equations from an implementation in terms of our queues, etc. That's what we show in the paper. We're getting compile time information about runtime behavior based on a simple and easy to understand model using types to expose the structure. And when you put this together with the work that we previously done, what happens is you can automatically rewrite programs to minimize costs for a parallel system under type control, just changing the type. We accurately predict lower bounds on speedups, and we verified that empirically, and we can choose between different alternative parallel implementations. So you can use this to reason about the parallelism in your program, work out which one is best in a provably correct way. So you can choose different patterns for implementation, or you can say, well, actually, say I wanted some of the processors to be CPUs, some others to be GPUs, or say I had many, many cores, all of them very lightweight, and a few big ones, which are much heavier weight. What's the best implementation in that situation? It's research. There's lots more to do. We've shown you some important common patterns, but lots of other ones that people are interested in too, things like stencils, bulk synchronous parallelism. What we would like to do is to be able to show that essentially all of the interesting parallel patterns that people have come up with over the last 40 years or so can be described in terms of hylomorphisms. That would be a lot of fun. We might need to investigate even more general recursion patterns than hylomorphisms. So maybe adjoint folds or conjugate hylomorphisms. And for heaven's sake, don't ask me what they are. Derived wrote that. And what we really want to do is to take this stuff, which I've described fairly abstractly in a prototype, and we want to apply this to a real language, Haskell, Erlang, etc., etc. The work is sponsored by an EU Horizon 2020 project that we're running. Our website, so I'm coordinating this project, halfway through it. Website is on the front page of the slides, which I will give to the audience. And I'm very pleased to say that we've received £500,000. It looks more impressive if you put it in zlotys. So 2.5 million zlotys to look into commercialization of these things. And what we're doing at the moment, initially, is we're looking at commercialization for C and C++, because we think we can make a real difference to those guys. We think they really, really, really need our help. And we have good functional technology that will help them. And they're coming in our direction too. C++ isn't an object-oriented language. It is a multi-paradigm language with functional features. They're moving towards ours. Java's moving towards ours. Scala is definitely functional, right? This is the future. Swift is functional. The future is functional, guys. Thank you very much.